SRM committee for organizing this interesting interesting lectures and inviting me to present. Okay. So I'll try to go very quickly, and let's hope that I can finish on time. So the classification of radiation. Radiation is classified into two main categories: non-ionizing radiation, and that's radiation that cannot ionize matter, and ionizing radiation, which is neutrons, protons, alpha particles, as well as heavy ions. Indirectly ionizing radiation is the second category, and those are for neutral particles, and that includes photons that are capable of ionizing matter, such as X-rays, gamma rays, as well as neutrons. So for charged particles, how do charged particles interact with matter? They interact with matter through basically two categories. One category is collisional interactions, that's interactions with orbital electrons, and radiative interactions or radiative collisions, that's interactions of charged particles with the nucleus. And the collisional interactions could be also divided into soft collisions and hard collisions. So for soft collisions, the charged particle the impact parameter, or the distance between the charged particle and the atom, is larger, much larger than the size of the atom. And that's the impact parameter. And in this case, the Coulomb interactions between the charged particle will be with the orbital electrons, providing them with small amount of energies. A hard collision is when the impact parameter of the charged particle is of the order of the atom size. And in this case, then a single interaction by the charged particle could actually transfer a lot of energy to one of the orbital electrons. And the third, radiative collisions, that's when the impact parameter of the charged particle with the atom is much smaller than the radius or the size of the atom. And essentially, the charged particle then will interact with the nucleus. In most cases, the interactions are elastic scattering, but about 1% of these interactions are inelastic, where the charge of photon. Interactions of charged particles, they are defined or quantified using stopping powers. And stopping power is basically the rate of the energy loss per unit path length of the charged particle in the absorbing medium. And more interestingly is the mass stopping power. That's just to include or to remove actually the density of the material from how charged particles lose energy in matter, and it's just the rate of energy transfer per unit length divided by the density of the medium. Part. And the total stopping power is just the sum of the energy loss from the charged particle through collisions and the sum of the energy loss per unit length or per mass through radiation. So this is just to summarize the collision interactions. It's an inelastic collisions between the charged particle orbital electrons, and in this case the atom could be either ionized, where an orbital electron is ejected, or the atom could be energy transferred to tightly bound electrons to raise them to higher levels. Radiative stopping powers is basically a Coulomb interaction of the incident charged particle with the nucleus, resulting most of the time in scattering. So the charged particle will just be deflected, no energy loss. But in some situations, the interaction will be inelastic, and the charged particle will lose its energy in the form of photons. It's important to note that radiative stopping power is inversely proportional to the mass of the particle. Thus, the radiative or Brahms-Chalang emission by, let's say, protons and alpha particles or heavy ions, these are, although they are present, they are negligible and could be practically omitted. But radiative stopping powers are important for and positrons. This is a graph of the mass stopping powers as a function of the kinetic energy of the part. As this, the bottom graph is for protons. And in general, the mass collision stopping power depends obviously on the kinetic energy of the particle, but it does not depend on the Z of the material. It depends on the electron density of the material. So energies, the collision stopping power is, and then as the energy of the charged particle increases, then the collision stopping power will slowly increase. The radiative stopping power, on the other hand, as I mentioned, is only for we consider it only for light charged particles. Depends again on the kinetic energy of the particle, and it depends on the atomic number Z of the number Z of the material. Thus, Brahms-Chalang production radiative loss is more efficient for high energy electrons. As you can see, as the energy increases, the radiative stopping power increases as well as Z. Here we have the collision stopping, the radiative stopping power for water, whereas this curve represents the collision stopping power, radiative stopping power for lead. The linear energy transfer is another concept that is usually used in radiobiology or in radiation protection to specify the quality of an ionizing radiation beam. And it has usually is given in units of keV per micrometers. Since the charged particle, they lose. So for heavy charged particles, the range and the medium is approximately equal to what we call the continuous slowing down, the range using or assuming the continuous slowing down approximation, where the charged particle just goes in a straight line and it's not deflected. However, for light charged particles, they're scattered in the medium. So electrons and positrons these particles in the medium is usually less than the range, assuming the continuous slowing down approximation. Of the initial kinetic energy of the charged particle that is emitted as photon. And obviously, this is only for light charged particles. And as the energy of the kinetic energy increases, then the radiation yield will increase. For photons, there are several interactions, so I'll go through them quickly. Photoelectric effect is the first interaction. It's an interaction of the photon with an atom, where the photon is completely absorbed and the energy is given to a tightly bound electron. And this tightly bound electron is emitted from the atom. It's called a photoelectron. The energy transfer from the photon to the charged particles is usually given by this formula. It's bounded by the photon energy minus the binding energy of the photoelectron. But remember, there is a vacancy going to be created, so we expect that there are going to be J electrons also emitted following the photoelectric effect. The cross-section or the probability of this interaction is basically it decreases as a function of energy. At low energies, the decrease is proportional to the photon energy to the power 3, but at higher photon energies, then still decreases, but as a function of 1 over the photon energy. It also, the probability or the atomic cross-section is proportional to atomic number of the absorber and estimated to be between proportional to Z to the power 4 and 5. We also observe in photoelectric or in the cross-sections for photoelectric effect that there are discontinuities. Those are binding energies of the shell, binding energies of the electrons or the shell energies. Compton scattering, that's probably the most important interaction for us in radio. For practical reasons, one can assume that this electron is not bound to the atom, and the electron is stationary. Although theta, and the scattered photon will have an energy lower than the incident photon energy. Using the laws of conservation of energy, relating the energy of the scattered photon to the energy of the incident photon. And the general rule is that the scattering angle of the photon is always going to be between 0 and 180. At 180, that's called a backscatter photons. And the recoil electron to be at an angle between 0 and increase. For Compton, so the general rule is that at very low energies, then the probability of the scattered photon being in the forward and the backward directions are equal. However, as the photon energy increases, then as the scattered photon is likely to be more in the forward direction. And this is the maximum possible energy transfer, or the maximum possible scattered photon energy. We can use this formula and set, for example, at theta equals to 180. This will show this, and we plot the energy of the scattered photon with the incident photon, and it comes to approaches a value of MEC squared over 2. So in general, the backscatter photon can never have an energy greater than 0.255 MeV, regardless of the incident photon energy. For the energy transfer, this is a very famous graph that plots the mean energy transfer to electrons as a function of the incident photon energy. The cross-section for Compton scattering, the atomic cross-section is proportional to Z. Obviously, as there are expect that the atomic cross-section to be proportional to the number of electrons, but in general, that decrease with energy as the energy increases. For the part here at very low energy, also that the atomic cross-section decreases. Or is lower than its maximum value, and this is due to the binding effects of the electrons. So at these energies, not all of the electrons available in the atom can interact through Compton. Rayleigh scattering is a photon interaction with the whole atom, and it's an elastic scattering. So the photon is just scattered with the same energy, and no energy is transferred to electrons or charged particles. Similar to Compton, at very low energies, the probability of forward and back scatter for Rayleigh are equal, but with increasing photon energy, the probability of forward scattering increases. And the cross-section for Rayleigh scattering, so it decreases with the photon energy squared, and is proportional to Z squared of the medium. So I'm talking about atomic cross-sections here. And in general, at low energies, Rayleigh scattering has a higher cross-section than Compton, but at higher energies, Compton scattering has a higher probability than Rayleigh scattering. Pair production is basically when a photon interacts with the electric field of the nucleus, and in this case, the photon disappears, and an electron-boson pair is created. So I apologize for this. Okay. So let me check that. Is my audio there? Yeah. Am I back? Can you see me? Can they see the slides? Hello?
Yes, we can hear. We can hear you.
Okay.
Yes, Dr. Omid, we can see the slide and we can hear.
Okay.
You.
Okay. So for pair production, one thing that is different for pair production than the other photon interactions is that it has a threshold. That means that photon energy is below this threshold. This interaction will never happen. It's not possible.
Dr. Omid?
And that, yes. Can you hear me? Yeah. Okay. And the threshold is given by this relationship. In general, for nuclear pair production, the threshold is about triplet production. The threshold is 4 MEC squared. The energy transfer for pair production or triplet production is just given by this simple formula. It's the photon energy minus the energy required to create the in general, triplet production is much lower in terms of probability compared to pair. Usually ignore it, or we include it and we call that pair production. So this means that we can just write, the total pair production cross-section is the sum of the atomic pair production and atomic triplet production, and it's proportional to Z squared. And the general rule is that below this threshold, the cross-section is 0, but as the photon energy increases, we get the cross-section for pair production will increase also. And it increases, see here we have lead, and here we have hydrogen. So it has a Z squared dependence. Photonuclear interactions, that's the last one probably that I'll talk about, is basic interaction of, it's called sometimes photodisintegration. The photon interacts with the nucleus directly, and resulting from that interaction will be an emission of a neutron or a proton. And the atom is then transformed into a radioactive material. Usually it has a threshold below a threshold of order of 10 MeV or higher. But in general, the probability of photonuclear reactions is much smaller than that for other atomic interactions. Effects that follow photon interactions, many of these interactions, for example, photoelectric or Compton, vacancy is produced. And when a vacancy is produced, this is usually followed by relaxation of the atom, either emission of characteristic X-rays or emission of OJ electrons. For pair and triplet, since the positron is produced, the positron after loses its energy is going to interact or annihilate with one of the orbital electrons in the medium, and we get two annihilation photons of 0.511 MeV. Annihilation may also occur in flight, and in that case, we can have 1, 2, or 3 actually photons emitted. But most of the time, the annihilation will happen when the positron loses all of its energy. The mass and linear attenuation coefficients will depend on the photon energy and will depend also on the atomic number of the absorber. In general, low energies, photoelectric is the dominant interaction, Compton is intermediate range, and then high energies, we have pair production. So we can calculate the interaction weights based on the cross-sections for the individual interactions. And this is just a plot for carbon, where this curve is the interaction weight or probability for photoelect. This is for Compton, and the other one is for pair production. And these are for other elements. This line basically it plots the atomic number Z versus and Compton cross sections are equal to one another, whereas this line here shows when Compton and pair production are equal to one another. So these two lines divide just multiplied by NA over A. Essentially, it's the cross sections per gram from the atomic cross sections. And since we one or less than the dependence when it comes to atomic number, one order less than those for the atomic cross sections. And attenuation coefficient, if we multiply it by the density, then we get the famous thing, the linear attenuation coefficients, which then allows us to define or how, you know, and from there we or the mean free path for particular photon energy in a particular absorber. The mass energy transfer coefficient is basically we take the energy transfers from the different interactions and using the weights of these interactions, join them with the mass attenuation coefficient to get a curve that is the mass energy transfer coefficient. So is that we calculate what is the mean energy transfer to the to electrons. Using the interaction weights, we calculate the total mean energy transfer fraction beam in that particular medium. Note that the energy transfer for Rayleigh is always going to be 0. And multiplying this ratio of mean energy transfer divided by the multiplied by the attenuation coefficient, energy transfer coefficients, or the mass or the linear energy transfer coefficients. The mass energy absorption coefficient, we have the electrons produced from the interaction of the photons. The electrons will interact with the medium, and they might lose part of their energy as photons. And we want to, we don't want to include that in calculation of the mass energy absorption coefficient, because we're interested now in the absorbed dose in medium. And that is characterized with what is called the mean radiation fraction. So here is a plot of the mean radiation. Increases, then this radiation fraction is also going to increase. And using the energy, the radiation fraction, and convert the energy transfer into energy absorption coefficients. Do I have 5 minutes?
Omid?
Yes.
We have 1 minute, and then we'll have a couple minutes for Q&A.
Okay, then just very quickly for neutrons, interaction of neutrons. So the neutrons, they're classified into different different types depending on their kinetic energy. And the most important interaction for us is going to be elastic scattering with the neutron with the nucleus. And what's really important is that in general, nuclei, the neutron will never very small. Interacts with a small nuclei, that's hydrogen, then it loses a lot of its energy. And it's estimated that about 25 collisions are required to reduce a 1 MeV neutron to a thermal neutron, whereas it's required to approximately 2,000 collisions to reduce the same neutron when it in lead. So I'm going to stop here, Dr. Walid, and open the floor for questions for the audience.
Thank you, Dr. Wamid. If there are any questions from the audience, we have not received any questions in the Q&A. If there are any questions, you could ask right now. Otherwise, we will start the second lecture. We'll wait 30 seconds. If there are no questions, we'll start the second lecture by Dr. Wamid. Dr. Wamid?
Yes.
We can start the second one. If we get any questions in this lecture, we'll ask you at the end of the second one, just for the sake.
Okay.
Thank you.
Okay, so moving on to the next lecture is the introduction to crossing an area A. The fluence rate, so if we're talking about the number of particles crossing per unit area per time, that is just the fluence rate, or it's called the particle flux. The area A is often defined to be large the energy fluence. So these particles, they carry energy. So instead of counting the particles, then let's sum the energies that are carried out by these particles going through this sphere. And that's the energy fluence. So fluence is the energy carried by particles crossing area A. And the energy fluence rate is called the flux, and it's known, it's also called as the intensity. So basically, it's the energy carried by particles crossing the area A per time t. It has the SI unit for energy fluence is joules per centimeter squared, or a common unit in our field is going to be in MeV per centimeter squared. Per second. Exposure is another, it's one of the first quantities used to photons in it. It's defined for photons only, and it is defined in air. And the SI unit for exposure is the coulomb per kilogram, but the Rontgen is the customary and more commonly used unit for exposure, where 1 Rontgen equals to 2.58 times 10 to the power minus 4 coulombs per kilogram. The next quantity is the kerma. release in matter or in medium, and it's defined as the energy transferred per unit mass. So obviously, the KERMA is used for indirectly ionizing radiation for photons and for neutrons. If we get the energy fluence, we multiply that by the mass, the KERMA here. And the SI unit for KERMA is joules per kilogram, which is often called the gray. For neutrons, again, KERMA, we have KERMA for neutrons, and for part, instead of using the energy fluence, they use actually the particle fluence. So it's the particle fluence of the neutrons multiplied by a neutron KERMA factor here, the product of the two, the KERMA for neutron beams. Absorb those. Of course, this unit, very interesting for us, is defined as the energy absorbed per unit mass equals to E absorbed over M, and it's used for all ionizing radiation, photons, neutrons, charged particles, whatever. And it's also defined for in the fluence multiplied by the mass energy absorption coefficient for that medium and for that photon beam. And the SI unit for the dose is joules per kilogram, also known as the gray, but it had an old unit, which is called the rad. And 100 rad is equal to 1 grays. Equivalent dose, that's a unit used more for radiation protection, and is defined as the absorbed dose multiplied by a radiation weighting factor. Ionizing radiation. And the SI unit for equivalent dose is joules per kilogram again, but it has a special name called the sievert. And the old unit so cavity theory. So cavity basically a theory that allows us to calculate the dose in one medium here, for example, surrounded by another medium, into the dose into the same, let's say, volume or same point when the cavity medium is replaced by the surrounding medium. So that will allow us to relate the dose in this medium when the cavity is not there to the dose in the cavity. So there are a number of cavity theories. The large cavity theory is basically the dose. There are a few assumptions. The dose in the cavity is deposited by photons interacting in the cavity. Essentially, photons that are interacting in the medium, they do not contribute to the dose in this cavity here. And the electrons, so basically electrons outside of the cavity do not enter the cavity. So the dose in the cavity is only, it results only from the photons interacting in the cavity. And the size of the cavity is much greater than the mean electron range. So the electrons that are produced in the cavity, they do not exit the cavity, but they deposit all of their energy inside this cavity. And the last influence of the photons in the medium. In this case, then the dose in the medium mass energy absorption coefficients of the medium to cavity. Another theory is the small cavity theory, that's the Bragg-Ray, where the dose from the surrounding medium. So essentially, what this means is that photons do not interact in the cavity. So the dose in the cavity are a result of the electrons that are produced from the surrounding medium. Again, the cavity should not or does not perturb the fluence of the photons. And the secondary electrons that are produced outside of the cavity, they just cross the cavity. And the tertiary electrons, but the secondary electrons do not exit this cavity. So if these conditions are met, then we can relate the dose by the ratio of the collisional stopping power ratios, medium to cavity. Now, a small, that's called the Bragg-Ray cavity theory. Then Spencer ethics suggested that the Bragg-Ray cavity theory actually overestimates the dose. Some of these tertiary electrons, they will have sufficient energy to exit this cavity. So the dose that is going to be in the cavity is actually less than that predicted by or dictated by the Spencer ethics cavity theory. And in this case, then the dose to the medium base, sorry, this is Spencer ethics, is stopping powers for medium to cavities. That's how the dose in the medium is related to the dose in the cavity. So finally, we'll move on to radioactivity. So there are a number of radioactive decay modes. We can categorize them in 6 main categories. This heavy nucleus. And in this situation, then the atomic number of the parent nucleus will decrease by 2, and the atomic mass number is going to decrease by 4. And this often or commonly occurs in nuclei with Z greater than. This is an example. Radium decays into radon with an alpha particle. And we can calculate actually the decay energy just using the masses of the parent daughter and the alpha particle mass. The alphas that are coming out from the nuclei, they will always have the same energy. So just have a spectrum with alpha monoenergetic monoenergy. This is the example for radon with the energy level diagram from radium decay into radon. Usually happens when we have a lot of neutrons in the nucleus. So in this case, the neutron base. And when this happens, we get an emission of an electron and an antineutrino from the nucleus. In this situation, the atomic number of the parent will increase by 1, but the atomic mass number will remain the same. These are examples. Cobalt-60 is an important radionuclide in radiotherapy. It actually undergoes beta decay to nickel-60. Again, we have cesium and iridium-192. All of these radioisotopes are used in radiotherapy. One aspect about beta decay, so we'll move on to beta minus. Beta minus is the opposite, is when we have a nucleus with proton, it's a proton-rich nucleus. We have a lot of protons than necessary. In this situation, a proton will transform into a neutron. And when this happens, we get a positron emitted from the nucleus as well as a neutrino. And the atomic number of the parent will decrease by 1, but the atomic mass number remains the same. These are very important radionuclides that are used in nuclear medicine, in 18 especially, that's FGG, where basically transformed into oxygen 18, and we get the positron and neutrino. These are the decay schemes for the fluorine and for nitrogen. So since in beta plus or beta minus decays, we get an electron and a neutrino, the beta particle that are coming out from the nucleus will not have the same energy for all decays, but we'll get a spectrum, and the spectrum in general will have this shape. So notice that a charge effect will alter or will change or will alter the spectrum for electrons or beta minus and for beta plus. As a beta minus particle is emitted, then the nucleus is, it's a massive positive charge. It's going to actually take some of its energy, and that's why we more lower energy beta particles. Whereas for beta plus, it's the opposite. A positron positive charge, it will be repelled by the nucleus, gain actually more energy than from what it acquired from the decay. Electron capture is another radioactive decay where the nucleus captures the atomic. One important thing I should mention also for the beta plus decay is that in order for this decay to happen, you need to have at least a difference in mass between the parent and the daughter of more than 2 MeC squared. So what happens when the parent and daughter, we don't have 2 MeC squared in terms of mass difference, then and you still have a lot of protons than required, then the nucleus may undergo what's called an electron capture. And in this case, a proton will just take one of the orbital electrons, becomes a neutron, and a neutrino is in this case, the atomic number of the parent will decrease by 1, but the atomic mass number will remain the same. These are examples. Iridium-192 again can decay through electron capture, and beryllium also is another radionuclide that undergoes electron capture. These are the decay schemes for iridium-192. Notice that iridium-192 can either go to undergo beta minus or electron capture in this decay. And of course, the photon are used actually for treatments. Decay, we just have a nucleus with a lot of energy, and then the nucleus decides and a photon is emitted from the nucleus. In this situation, the atomic number Z as well as the atomic mass number do not change. Example would be technetium-99m that decays into technetium-99, emitting a gamma. So the Z and the A will remain the same. Internal conversion is something similar to the gamma emission, where basically instead of emitting the gamma, the nucleus decides to give that excess energy to one of the orbital electrons, and the electron then is ejected with from the atom, and that is called internal conversion. Again, the atomic number and the atomic mass, they remain the same. But in this situation, a vacancy is produced, and then the atom will undergo some either by emission of characteristic X-rays or through OJ electrons. These are examples. Again, technetium may also undergo beta internal conversion, not just a gamma emission. And then we have spontaneous fission. So basically, a neutron is captured by a massive nucleus, and the nucleus will then split into two or more large nuclei, and as well as maybe neutrons come out from this decay. And this decay scheme competes with alpha decay, since it's usually present for high Z nuclei, and the higher the A, the more predominant is the spontaneous fission in comparison to alpha decay. Examples would be uranium-238. The half-life for spontaneous fission is about 10 to the power 16 years, while the half-life for alpha decay is 4.5, 10 to the power 9 years. So for uranium, it's actually, we get spontaneous alpha decay is more probable. But for fermium, for example, it's the opposite. So spontaneous fission is about probability of spontaneous fission after capturing this neutron decay. Some nuclei may be neutron rich, and they decide to, okay, I'm gonna give up 1 neutrons, and the neutron is emitted. This is not observed in nature, but through artificially produced radionuclides may actually undergo neutron this is an example, helium-5, for example. This is not a naturally occurring radioactive. It will undergo just a neutron decay, transforming to helium-4 and a neutron. Proton decay is also another decay scheme where we have a proton-rich radioactive material, and in this case, the parent nuclide may emit a proton or 2 protons or more through this decay. These are examples: lithium-5 becoming helium-4 through emission of 1 proton, and then we have iron-45. In this decay, it will emit actually 2 protons there. The kinetics of radioactive decay, parent-daughter decay, where we can, this is the first order differential equation that describes the kinematics of decay. And at the end, when we solve the equation, we get these 2 very famous equations that I'm sure all of you know. Is relating the number of nucleides of a parent to an initial value by this exponential factor, or activity to the initial activity. So the parent activity, this is how when we plot it as a function of time, we get this exponential decay, and from it we can have the concepts of half-life, mean life. So a half-life, by definition, is just the time required that the activity is reduced to 1/2 of its initial value, and the mean lifetime is just given by this relationship. It's the reciprocal of the decay constant. Finally, we have this general, when we have a parent-daughter, granddaughter decay scheme. So the daughter now, we're not interested in the activity of the parent, but the activity of the daughter. Again, we set up these differential equations, and we get from the solution, then it's the equations that describe the activity of the daughter as a function of time. And in general, this is how it looks like. So here, this is the activity of the parent. It's just an exponential decay, but the activity of the daughter initially is 0, and the activity grows until it reaches a maximum, and then will decrease. And the maximum daughter activity, that's when occurs at this point here. This is called the characteristic time, and it's given by this relationship where, and it's related to the half-lives of the parent and the daughter. So we have this, for this parent-daughter, granddaughter situation, we have what's called equilibrium. We look at the activity of the daughter in comparison to the activity of the parent. And in many situations, that the activity of the daughter as time, after a certain time, then it will reach this constant value. And this is independent of further increase in time. So let me just go through this quickly. So this is a situation where we have transit equilibrium. So after the daughter has grown, and now it's decreasing, the activity of the daughter is somewhat related to the activity of the parent. It will decay with the same, let's say, rate or proportional to the rate of that. And that's the situation, we call it the transit equilibrium. And this happens in general when the half-life of the daughter is less than the half-life of the parent. Another half-life of the daughter is much smaller than the half-life of the parent. Then we get what's called the cyclic equilibrium, where the activity of the daughter is actually equal to the activity of the parent. And the last equilibrium, or no equilibrium, that is when that occurs when then the half-life of the daughter is greater than the half-life of the parent. In this case, we will never get an equilibrium between the two. So we will always find that the activity of the daughter in comparison to the activity, or the ratio of activity daughter and parent, is just going to increase as time increases. So this is my last slide, Dr. Walid, and I'm going to stop here.